Very good morning to all of you and welcome to this 9th session on signals and systems. Well, we are now coming to the final part, the last 2 sessions of our expositions, the instructor's expositions. So, I would be giving you expositions in this session and the following session, right, following which in the subsequent sessions when you have them on signals and systems, you will be carrying out peer learning activities, right, and also you will be examined, you will put across what you have understood through the sessions that we have conducted, right. Now, first and foremost, what is the final verdict on being able, I thought you must have slept over it and thought over it, right. So, what is the final verdict on being able to find out R and C in this network? Can you do it by measuring the current on the capacitor? So yes, you can. How would you do it?
You will have to take 2 current.
Okay. Very nice. So can you come and justify it?
First one will be I equals to V into R e to the minus t 1 by tau, and V is fixed, so we can just take it 1. Okay, so then I1 will be there, I2 will be 1 by R e raised to the minus t2 by tau, and by just dividing it, we will get, because we have measured this, so we will have one number I which we have, because we have measured these, so that's why we will get a number here, and these R will be crossed out, and we will get e raised to the power, because this is minus t1, when we divide it, this minus t2 will be plus t2, so it will be t2 minus t1 by tau. Okay, so we know t1, we know t2, from there we can calculate tau. So we will get tau here, and from putting tau in here, we have tau, we have t2, we have R, sorry, we don't have R, we have I2. We can calculate R from here.
Agree with him? Yes, I think we should all wake each other up, right? That's very correct. So actually you can indeed calculate the resistance and capacitance with 2 measurements, right? And the mistake that I was making yesterday was that I was what was the mistake I was making yesterday? You saw what I said, that it depends only on tau. But what depends only on tau? It's the impulse response of the circuit which depends only on the tau. Also the impulse response is proportional, it's commensurate with the current, but the impulse response is not equal to the current, right? The impulse response multiplied by the capacitance value is the current. Is that right? So all these vacillations, but when you're framing a question, these are, in a way it illustrates how there could be many different considerations that you need to exercise when framing a question, and often the difference between a correct and a wrong statement of the question can depend on what you're asking, right? So if you're asking for the current, then of course you can determine both the quantities R and C based on 2 measurements. If you're looking at the impulse response, you cannot, right? Anyway, now, yes, please. Yeah, the specification, when, as long as they are distinct, and yes, they must of course be more than 0, because what he is written is for T1, T2 greater than or equal to 0. In fact, it may be useful to choose one of them equal to 0, because then you get R directly, right? And you can choose the other one to be anything, and that will tell you the value of C, right? So you can indeed calculate both those quantities. Now let us embark. So this was module 3. Now what this was meant to illustrate is that if I know a priori which waveform I am sampling, right? If I know a priori which waveform I am sampling, then I can do with less measurements than what is prescribed by the Nyquist sampling theorem. In fact, here I needed, if you have I told you, if you have a constant voltage, you need only 1 measurement. If you know that the voltage is like this, comes from the output of an RC circuit, right? Or if you know that you are looking at the current in the RC circuit or the current in the resistance or the capacitance, does not matter, then you can make do with a finite number, 2 measurements, right. And similarly, so in fact, what in some sense the whole field of sampling and reconstruction, is a game of a priori knowledge versus measurement. The more the a priori knowledge that you have, the less the measurement that you need, right. And in particular, what you learn in the Nyquist sampling theorem is that if you have a band limited signal, that is the a priori knowledge, the signal is band limited, then you also need to know, you see, what is the other a priori knowledge you need to have? If you know a signal is band limited, but you do not know its band limit, then again there is a problem, right. But if you know a signal is band limited and if you know where its band is limited, then you can of course formulate a sampling theorem and reconstruct from the samples. Is that right? Anyway, all this constitutes module 3. So, when I teach a course on signals and systems, all this constitutes module 3, the third module on sampling and reconstruction. And in fact, there are other topics in the sampling and reconstruction module. I must once again repeat that you must make use of the video playlist that is available to you. How many of you have by now accessed Moodle? Can you raise your hands? Yeah. Oh, you don't have internet access? All right. But then of course that problem can be corrected by our office. But how many of you, so how did you people access the Moodle? Through the mobile. Okay. Through the mobile you were able to access the INA Moodle. And how many of you have looked at my course outline? Yeah, many of you have seen the course outline and you've seen there's a playlist there. So you must make use of that playlist, right, to learn the topics in more depth. Is that right? So you have access to the playlist, isn't it? You must make use. So here I have, within the time that I have touched upon all that is needed to embark upon the journey. I can't possibly do what has to be done in 30 lectures in 10, in 12, in whatever, 12 sessions, isn't it? So I have given you what is required to embark upon the journey, and you must now of course complete the journey on your own. And of course all this will help you frame the course outline, a revised course outline when you are asked to, right, in the sessions following my sessions now. Anyway, now we come to the fourth module of this course. We deal with more general transforms. We were looking at the Fourier transform over the past few sessions, isn't it? And now we are looking at the intent here, the fourth module, is to look at transforms that can deal with a wider class of signals. What was the problem with the Fourier transform? All signals do not have a Fourier transform, right? You took the example of an exponentially growing signal whose Fourier transform does not converge. Now, there are also, when you go deeper, you realize there are also signals which have a Fourier transform in a restricted sense. For example, if you take the unit step, we often do associate a Fourier transform with it. But the Fourier transform would require impulses in the Fourier transform. If you take a periodic signal, which is a sum of sinusoids, again, we do associate a Fourier transform with it. Although, strictly speaking, the Fourier transform would not converge. But the Fourier transform must incorporate impulses. So, sometimes by bringing in generalized functions, one can extend the Fourier transform to a broader context than is immediately possible with simple functions like the decaying exponential and so on and so forth, right. Having said that, there are still functions where we cannot at all deal with the Fourier transform. And an example we took yesterday was the growing exponential. There is no way we can deal with the Fourier transform for a growing exponential, right? There is no accommodation with impulses, nothing would work there. And therefore, there we need to be able to deal with such functions. Now, you see, we saw some of the advantages of the Fourier transform. One advantage we saw is that convolution gets translated into multiplication. So, if you convolve two functions and both of them have a Fourier transform, and you are assured that the output also, the output of convolution also has a Fourier transform, then the Fourier transform of the convolved function is the product of the Fourier transforms of the individual functions which are being convolved. So, convolution in the time domain translates into multiplication in the Fourier domain, right. So, this is, see, multiplication as an operation is much easier to understand. Further, multiplication is pointwise, right. So, it is a pointwise operation, which means that sinusoidal, each complex exponential component is treated independently, it is treated in a decoupled manner. So, decoupling of different complex exponential components happens in the Fourier transform, right. It is as if the Fourier transform decouples the effect for each component. For a linear shift invariant system whose impulse response has a Fourier transform. By the way, if a linear shift invariant system with impulse response ht, which has, if ht has a Fourier transform, then this Fourier transform is called the frequency response of the system. In fact, the frequency response of the system tells you how the system behaves with sinusoidal inputs. Of course, it can be seen as behaving with complex exponential inputs, but then you know that a sinusoid is comprised of complex exponentials, so you can always extrapolate what it does to the complex exponential to what it does to sinusoids, right. So, the frequency response of a linear shift invariant system is defined if its impulse response has a Fourier transform, right. And we saw the example of the RC circuit. There we could obtain the frequency response either directly by voltage division or circuit analysis, and also through the impulse response, right. So, we must interconnect these ideas. Anyway, now we are asking what to do when the function does not have a Fourier transform. Well, let us take the case of the growing exponential. So, e raised to the power, let us take e raised to the power 40 ut. Okay. Now, e raised to the power 40 ut, of course, begins with 1 at t equal to 0 and grows, and the Fourier transform does not converge at any value of the frequency, right. So, now how would we deal with such a function if we still want to take advantage of the property of convolution, for example, or if you wish to be able to generalize the Fourier transform in such a way that it can incorporate this particular function as well. Okay. Yes. Yeah, any ideas? Because that's interesting. If you say you can use the Laplace transform, you are absolutely correct. Okay. All right. So, where does it converge? What is to converge and where does it?
It can converge below 0.
Yes. That's very correct. Why don't you come and explain what you're saying? It's very nice. It's a very good insight. Yes.
As this signal is growing exponential, if we multiply this with decaying exponential, then it will decay. But suppose it is growing by 4, if I multiply with 3 minus 3, it will not decay.
Yes.
So we have to determine that particular constant for which it will decay. In Laplace transform, we find the region of convergence. That is the value of that constant for which our signal is converging.
Yes, that's absolutely correct, actually. You see, so Vikash has correctly explained to you what needs to be done. In fact, this insight which he's given you is very critical. It's not enough, when we teach the Laplace transform or when we explain the Laplace transform, it's not simply appropriate to spew a formula out, What Vikash has explained right now is a very good insight, right? What are we doing? You have an exponentially growing function here. What do you do in the Laplace transform? You first multiply this exponentially growing function with another function, with another exponential which can capture its growth. Not only capture its growth, force it to decay. So in fact, the way to look at it is, I have this function e raised to the power 4t ut, right, or e raised to the power 4t for t greater than or equal to 0. I multiply this by e raised to the power sigma t, okay, and of course sigma t needs to be negative so that it can arrest the growth. So you see, you need to arrest the growth. To arrest the growth, okay, by multiplying by an exponential, and the exponential factor should be enough to arrest this growth. So as Vikash says, here 4 plus sigma should be less than 0, isn't it, to arrest the growth, which means sigma must be less than minus 4. Is that right? So once you've arrested the growth, then you can take the Fourier transform. So, if you want, we know that sigma needs to be negative. So we'll make this minus sigma and we'll say 4 minus sigma needs to be less than 0. Okay. So, of course, minus sigma needs to be less than minus 4. Sigma needs to be greater than 4. Okay. Now you can take its Fourier transform. So today I won't write capital omega 0 every time because I now appreciate that the angular frequency is a variable. Yesterday I wrote capital omega 0 because I want to specify, I want to begin with one particular value of the angular frequency, but now I'm just writing capital omega to capture the fact that it is meaningful for all frequencies. So now you see, I want this Fourier, this Fourier transform will certainly converge now because this has become exponentially decaying. So see, the ut is captured by integrating from 0 to infinity. So I am essentially noting that the function is non-zero only for time t greater than or equal to 0. Now let us look at this. You see here, you may rewrite this as summation 0 to infinity e raised to the power 4 minus s t dt. Okay. And let's see what it gives you. So it gives you e raised to the power 4 minus s, right, divided by 4 minus s, and you need this to go from 0 plus to infinity. So you see, now since you have taken s, now s is sigma plus j omega. It's a complex variable. if S obeys this, meaning sigma is greater than 4, right, then what do you have? You have e raised, so the upper limit at infinity, this must go towards 0 since it's an exponentially decaying waveform now, right, provided you have obeyed that requirement. And then at 0, of course, it becomes simply 1, and therefore this becomes 1 by s minus 4. Okay. Now this is generalizing the Fourier transform. So what are we doing here? We are first arresting the growth of a function which otherwise does not have a Fourier transform, and then we are taking the Fourier transform, right. First tame the function so that it can have a Fourier transform and then take its Fourier transform. So what is the Laplace transform? A Laplace transform, this is called the Laplace transform of e raised to the power 4 tut. But you see, the Laplace transform is not simply an expression. You must qualify it with a condition on S. What is the condition on S? The real part of S, which is sigma, must be greater than 4. So you must always qualify the expression with a condition on S. The condition on S is always an inequality, right? It's an inequality on, now let me ask you, look at what is happening here. Will that inequality operate on the real part of S, or will it operate on the imaginary part of S, and why? Yeah, it operates on the real part of S. Why? Because the imaginary part has no role to play in convergence. Why is that inequality being imposed? That inequality is being imposed to force convergence. So convergence is not at all influenced by the imaginary part. Okay, so it's only the real part which influences convergence, and therefore there's an inequality on the real part. So in general, when you have a condition on S, it is of the form sigma is in an inequality. So how does that look? This is the S plane, the complex plane. This is sigma, this is capital omega, and this is sigma equal to 4. Okay. Now, if sigma is equal to 4, what is that contour? What is that curve in the S plane? It's a straight line perpendicular to the horizontal, perpendicular to the real axis. Essentially, it's parallel to the imaginary axis, isn't it? Sigma equal to 4. And this is the region in which you must choose S. And this is therefore called the region of convergence. Or ROC. This is the region of convergence of the Laplace transform. So, a Laplace transform, it must be emphasized, is always an expression together with a region of convergence. You must never think of a Laplace transform only as an expression. In fact, we will also see why this is important, why we have to specify the region of convergence. You see, we may be tempted to think that if I see the expression, I will always associate a region of convergence with it. That's not true, right? Let me give you an exercise right away to see why this is not true. In fact, let me see, some of you must have taught and used the Laplace transform quite a bit. Let me ask you this question. Why is the region of convergence required to be specified? Or you know, can there be an ambiguity if the region of convergence is not specified? Let me pose the question that way. So, why the region of convergence needs to be specified is also clear from here, because you know that if it does not obey the region of convergence, then that integral will not converge. But you might be curious to ask whether, if I look at the expression, can I already associate a region of convergence with it? No, not so. Why do you say not so? Is there an ambiguity in it? Yes? Okay, very interesting. That's very interesting. Very good, very nice. That's absolutely correct. Would you like to come and explain what you said? Yeah, or maybe would you have the same? Anybody else? Yeah. Anybody? That's absolutely correct what you're saying. Why don't you come and explain? Yeah, please. It's not only is it required to specify the region of convergence because of the need of convergence, but also for another reason.
For this, we got this is our Laplace transform, and if you take minus 40 and minus ut, again we will get the same Laplace transform. So just by looking the Laplace transform, we cannot determine whether this is 40 or minus 40. So yeah.
Correct. That's absolutely, the idea is very correct.
So in order to distinguish, we need to look for this region of convergence. Region of convergence is here. That means it is the equivalent is this. If we do inverse Laplace transform, if we have this expression, then we may write this one, or you may write minus 40. So we may get confused. So in order to reproduce the original signal, just we have to look for region of convergence also. So we can calculate Laplace transform for this one also. And
why don't you do that? Why don't you calculate the Laplace transform of e raised to the power minus 4t u minus?
So then we have to take the limit from
somebody else volunteer. You can be a very good. That's fine. Shani will calculate the Laplace transform of e raised to the power minus 4t. Very good. That's a very correct way of thinking. But let's see.
So if we have e to the power minus 4t u minus t, now the integral will go from minus infinity to 0.
Yes.
Because u minus t is a step function like this, 0 and it's minus infinity.
Yes.
So now we will have e to the power minus 4t,
yes.
E to the power minus st, yes. u minus t is okay, dt is here. So we will get minus infinity to 0, e to the power minus 4 plus s.
Yes.
Okay. Then dt is here.
E to the power minus 4 plus s
into t. Yeah, obvious. Then we can have like e to the power minus 4 plus s into t limits minus infinity to 0 upon minus 4 plus s.
Yes.
Here it will be. So when it's 0, it will come 1 over minus 4 plus s.
Yes.
Okay, so it will be minus 1 upon s plus 4.
Yes.
Okay, and for minus infinity, it will become infinite. Sorry, so we will take e to the power 40. Sorry, it will be like this. If we are taking like that, then 4 minus s will be here. Now it will come. Okay, so if we are taking e to the power 40 u minus t, then we will get. Okay, yeah, it's okay. Now, so we have ut 40 u minus t. Yeah. 40. Yes. Yeah. So minus st, now it will be 4 minus s. We will have here 4 minus s. It will be 4 minus s, and then we will get 4 minus s.
Yeah.
Okay. Minus 4 minus s, and it will ultimately come upon 1 upon s minus 4. Just like we had e to the power 2.
Put a minus sign, right? So I mean, this is how you see. Very good. That's very good.
Now this region of convergence.
Yes, the region of convergence.
So now this region of convergence will be for 4 from here to this side, because here s was to capture its convergence, s should be less than 4.
Yes. So That's absolutely correct. That's why we sometimes learn more out of mistakes than we learn out of routine explanations. Is that right? So, here you now know what small correction is additionally needed. So, of course, as he said, e raised to the power minus 4t is not correct, right? You need e raised to the power 4tu minus t. But then even with e raised to the power 4tu minus t, you get minus 1 by or so you have a minus sign there, all right. So, you need to multiply this again by minus 1. So, once you take minus e raised to the power 4tu minus t, you get the same expression. You get the same expression, but with the region of convergence, real part of s less than 4, which as he says is this region. Is that right? So, e raised to the power 4t ut has the Laplace transform 1 by s minus 4 with a region of convergence real part of s greater than 4, essentially to the right side of the vertical line passing through sigma equal to 4. Minus e raised to the power 4tu minus t has the Laplace transform, same expression, 1 by s minus 4, but with a region of convergence real part of s less than 4. So, you see, now not only you see what is the importance of the region of convergence. Not only does the region of convergence tell you what is needed for the integral to converge, it also distinguishes between two possibilities. Of course, the number of possibilities is finite. In fact, the number of possibilities depends on how the plane is partitioned by the vertical line. Here the plane is partitioned into two regions. So, either of the two regions can be the region of convergence here, right. Now, this point sigma equal to 4 is called a singularity in the Laplace transform. Singularity means a point where that expression does not converge, the expression is undefined. In fact, if you put as s tends to 4, what happens to this expression? This expression tends to infinity. So, this expression has a singularity at s equal to 4, right. Now, wherever there are singularities, those cannot be a part of the region of convergence. So, how do we identify regions of possible regions of convergence? Excluding the singularities. Look at vertical lines passing through the singularities and which are the possible regions of convergence? All the regions between these vertical lines, right. Let us take another example. Now, what we'll do is, we'll go the other way. We went from the function to the Laplace transform. Let's go from the Laplace transform to the function and let's see what the possibilities are. So, let's take the example of the following Laplace transform. 1 by s plus 4 into s minus 4, which is in fact 1 by s squared minus 16. Now, I wish that you should first on your notebook sketch the S-plane, mark the singularities of this and tell me how many possible regions of convergence you can have. And then I would like volunteers to come and solve it. So, you understand the question? I draw the S-plane, mark the singularities of this function, which is what are the places where there are singularities, right? And then identify the possible regions of convergence. So, how will you identify the possible regions of convergence? Those regions must exclude the singularities, right? They must exclude the singularities. And of course, the regions of convergence are related only to the real part of S, which means they must be between vertical lines, right? So, now, any volunteer to solve? You volunteer? Very good, yes. Shami has always been very kind to me, yes, come. Very good, yeah, why don't you come and explain?
Simply as we have, okay, not about the poles, but we have for plus 4, real part and one for minus. So there will be two lines here. So we have three region of convergence. One is between them, one is right side them, and third is left side. So this, and this. Three region of convergence will be there.
That's one. Now, the next question that I have, where I again invite some volunteers, is I want to invert this Laplace transform. Inverting a Laplace transform, you see, finding a Laplace transform can be a process of simple integration, as you see. Inverting a Laplace transform is a game of experience often. It can be done also by integration, but that's not the most common way of doing it, right? So, inverting the Laplace transform is done by experience, by experience of having calculated many Laplace transforms. So, look at the form and you find the inverse. That's how we normally go about it, right? So, here I have three possible regions of convergence and I have this expression. Now, I have calculated a Laplace transform there. I wish that you should tell me how you can invert this Laplace transform, each of these three regions of convergence. What strategy will I follow to take advantage of what I already know? In fact, now let me ask an easier question first. You calculated the Laplace transform of e raised to the power 4t ut there, right? And you also calculate the Laplace transform of e raised to the power minus e raised to the power 4t u minus t, isn't it? Let's generalize. Suppose you have e raised to the power alpha t ut. And we'll use this symbol, script L means the Laplace transform. So, what is the Laplace transform of e raised to the power alpha t ut in general? 1 upon s minus alpha, and with what region of convergence? Real part of s, yes, real part of s greater than, now, should I say alpha or should I say real part of alpha? Isn't it? The imaginary part of alpha plays no role. So, real part of s greater than real part of alpha, because alpha could be complex as well. Is that right? Now, what is the Laplace transform of e raised to the power alpha t u of minus t? Tell me, what is the Laplace transform? Be careful. E raised to the power alpha t u of minus t. 1 upon, yes, minus 1 by alpha minus s minus alpha. And with what region of convergence? Real part of s is less than real part of alpha. Yes. So, this is a generalization, isn't it? This you can calculate yourself. So, it's a generalization. Now, I want you to solve this. How will I solve this? How will I solve for partial fractions? Please tell me the partial fraction expansion. Yes, tell me.
So our function is 1 divided by s plus 4 into s minus 4. So we have to make it partial fraction. So a divided by s plus 4 plus b divided by s minus 4. So now we have to find out a and b. So there are different methods. So here I will go for directly the method. So a is equal to 1 divided by s plus 4 into s minus 4 whole into s plus 4 at s is equal to minus 4. Yeah. So this will cancel. So we will get 1 divided by s minus 4 at s is equal to minus 4. So if we will substitute this value, I will get this minus 4 minus 4. So this is minus 1 by 8. So this is one value a, and similarly if we will find b, so this is 1 divided by s plus 4 into s minus 4 multiplied with s minus 4 at s is equal to 4. So we will get the value as s is equal to s plus 4 at s is equal to 4. So we will get 1 divided by 8. So I will get now 1 divided by s plus 4 into 1 minus s minus 4, which is equal to minus 1 by 8 divided by s plus 4 plus 1 divided by 8 divided by s minus 4. If we are taking common 1 by 8, so 1 by 8 whole into 1 divided by s minus 4 minus 1 divided by s plus 4. So this is the partial fraction form.
Now what will we do with these? The Laplace transform, very good. Would you like to continue now? Would you like to find the inverse in each of them?
Yes.
Yes.
So if we will find out its inverse, so that is if we will separate it, it will satisfy the linearity property. So 1 divided by s minus 4 minus 1 divided by 8, 1 divided by s plus 4. If we will find out its inverse Laplace transform, so directly we will get 1 by 8, this is e to the power 4t u of t, and this is 1 divided by 8 e to the power minus 4t u of t.
Now is this applicable for all the regions of convergence? Or
No, so now we have to find out the ROC. So in this case, the first one, the ROC is ROC of s, which is greater than, that is 4. So this is the ROC of first one, and the ROC of the second one is real of s, which is greater than minus 4.
Yes.
So now we'll get two ROC. Now you have to find out the intersection of these two
What is
ROC.
the intersection? What is the intersection?
So the intersection is ROC. So now we have to draw it. So now first one is, so this is 4, and the second one is, this is minus 4. So the first ROC is greater than 4. So this is the region greater than 4. And the second ROC is greater than minus 4. So this is the region greater than minus 4. Now we have to find out the intersection. What is the intersection common part? ROC is greater than 4. So the total overall ROC is real of s greater than 4.
Yes, I think that's good. You've learned. So you've learned my techniques. Yes, good. There can be, oh, you feel you can have 4 ROCs. Oh, what are the 4 of them?
The whole entire thing excluding minus 4.
Oh, so okay, that's interesting. Shami says now he has 4. Yeah, would you like to come and explain which 4 there are? Come. That's a good idea, yeah. That's a good point. Yes.
Actually, the other 3 were same. This one, and this one.
Yes.
And one will be the entire S plane excluding this plane, because we can't have singularity in our ROC, so that's why this part will be removed, and we will have one ROC going here and here. We can have both of them, because by the look of it we have 2 components here, and for these 2 we can have, for both we can have 2 types of Laplace transform, inverse Laplace transform. So that's why 2 is to 2 is 4. So 4 types of transform we can have now.
That's the point actually.
So another ROC is in between that intersection.
No, that's yeah, it will be entire S plane excluding this part, because we have ROCs like that, if you remember in singles. Yeah, one is in between this, one is this side, second is this side, and the fourth one is entire S plane excluding these part.
Very good point actually, isn't it? So is he correct? Very good, well done. Yes. Why not? Yes. Good, sometimes it's good to be young people once again, and appreciate. Yes, he seems correct, no? It's a very good point. He seems quite right. So, Shami, what is the inverse Laplace transform in that region? The fourth one.
The fourth one,
There is only one valid inverse one. Right side of minus 4, left side of plus 4. This is only valid. It should be valid for both.
the inverse Laplace transform for that will be minus e to the power.
Okay, so Shami has an answer. Yeah. Tell me, Shami, what is the answer?
Minus
Yes, minus. Yes.
4tu minus t
4tu minus t
plus
plus
e to the power 4tu.
e to the power 4tu t. Let me see. That's very interesting. So e minus e raised to the power 4tu minus t. So
No, 4t.
4t. Okay. So here this would have a Laplace transform, which is a form real part of s less than. So it should be minus 4, is it? Okay, I see. Very good. Well, let's do one thing. So, what he's raised is a very important point. See, in fact, what he's raised is a very important point. It's a very subtle point about Laplace transforms. See, as he says, it looks like if you take those two regions and take their union, then that also excludes all singularities. It seems like that. That should be a region. So, is there an inverse in that region? It's a very good point. What we'll do is I won't answer the question, right? Rather, what I'll do is now we have a tea break, no? So during the tea break, you can think. There should be think about it, and then after the tea break, we'll see if we have an answer to this. But it's a very interesting. Now shall I? I won't answer the question. I'll confuse you even more now, right? Should I do that? I'll confuse you even more. Let me now look at further confusion. Sometimes, instead of answering questions, instead of removing confusions, sometimes it's good to increase the confusion. Is that right? So that, you start thinking more. Further confusion. As teachers, you should think about this. See, suppose I take e raised to the power 2t ut plus e raised to the power 2t u minus t. Does it have a Laplace transform? It has a Laplace transform, right? What is its Laplace transform? So Shami says that this has a Laplace transform. So as I said, now all this time I've been trying to reduce your confusion. Now I will try to increase your confusion little more, right? So now I've left you with this confusion. Now we can all go and have a cup of tea. Now I've increased your confusion a bit, right? So now I have this function e raised to the power of 2t ut plus e raised to the power 2t u minus t. Question is, does it have a Laplace transform? If so, what is its Laplace transform? Right? That is a profound thing. All right, we'll have a little break for tea and we'll reassemble after tea at 11:15. 11:15.
Okay, I am Sitanshu Sekhar Sahu. So I am a faculty in Department of Electronics and Communication Engineering at Birla Institute of Technology, Mesra, Ranchi. So I teach signal and system last 3 to 4 years. Thank you.
Hello, I am Dr. M.G. Srinivas from Maharaja Institute of Technology, Tandavpura. I have taught signals and system 5 times, and my subjects are basic electronics and control systems. Thank you.
Good afternoon. I am Shamim Ahmed and I am from a town called Ghaziabad near Delhi. And currently I am teaching in MMA and TC Malegaon. I have taught this subject only one time, that too online. But this was my favorite subject when I was graduating.
I am Dr. Vikas Singh. I am Associate Professor in Manipal Institute of Technology, Manipal.
Good afternoon, one and all. Myself, Dr. Saurabh Mitra. I am working as a professor in Gopte Institute of Technology, Belgaum, Karnataka. I have taught this courses few times.
Myself, Shilpa Medkar. I am working with Department of Electronics and Telecommunication, COP Technology University, Pune, and taught this subject 4 or 5 times. Thank you.
Thank you so much. So you are in very able hands now, right? These 6 people will, conduct your teaching sessions. In addition, my teaching associates will be there, and they'll also be supervising and and they'll be steering the sessions. Is that right? And my teaching associates might also pose some questions once in a while, and also pose problems to you, and they will also be evaluating your responses. Is that right? Later. And of course, you know my teaching associates already. There's one more, Rupanjan, he might also join, depending on what he wants to do. Anyway, these 4 are there. And you have 6 sessions which you must now conduct, and we'll be recording those sessions, and they'll be recorded as well, right? So that you can use them later for your benefit. Right? So all this. So very good. Then I'll conclude my session, and now we have the next instructor coming in. Oh, you want a group? Yeah, please, let's have a group photograph.